Very good. Welcome to session one of the Minnesota Space Grant 2021 Student Symposium. Our first speaker is Kai from Augsburg. Perhaps you can introduce yourself so I don't mess up your last name.
Yes, thank you, Dr. Flatten. My name's Heltemes, and I'm presenting on behalf of Augsburg University today. And I'm going to be basically presenting my slides here on the gating dynamics in ionic liquid gated FeS2 single crystals. Now, before I start my talk, I'd like to acknowledge the people that made this possible. I did this research over the summer of 2019 and through the fall of 2019. Notably, the MERSEC Foundation is responsible for funding me through the summer. And I also thank the Minnesota NASA Space Grant Consortium for funding me through the fall, as well as Augsburg University and University of Minnesota for allowing the facilities. So what I'm going to do first is I'm going to introduce everyone to the concept of electrolyte gating. Basically, what we have here is we have a typical field effect transistor, but instead of applying a normal metal oxide type of dielectric in there, what we're going to actually do here is we're going to be applying a dielectric that's basically an electrolyte. And all an electrolyte is in rudimentary terms is some salt dissolved in a solvent. One very common type of electrolyte I know everyone is familiar with is Gatorade. One of the benefits of having an electrolyte as our dielectric is that when we actually apply a gate voltage across this ionic liquid or this electrolyte, because the ions in solution are mobile, when we have electrons piling up on our conductor, the cations in the solution can actually come down to accommodate that charge. And what they do is they form this essentially a nanoscale parallel plate capacitor known as an EDL or an electric double layer. The benefit of the EDL is the fact that we get very, very small charge separation, approximately the size of the ions themselves. This induces very high capacitance into our sample, and it allows us to inject very large charge densities as well. So much so that we're actually able to control magnetic phase transitions in our sample, which we'll be very interested in the study. Now, obviously, we aren't just pouring Gatorade on a conductor and applying a gate voltage across it. We use something a little more complex known as an ionic liquid. All an ionic liquid is a molten organic salt at room temperature. And we like to use ionic liquids because of the fact that they have very wide electrochemical windows, allowing us to not worry about any electrochemistry mucking up our results. So I've introduced what electrolyte gating is. I'd like to show its context and research. And really, it breaks down into two main results that electrolyte gating has seen. That's the ability to control properties of a known ferromagnet and also to induce phase control in materials with some amount of finite spin, whether that be an ordered amount of spin, such as an antiferromagnet, or a disordered spin, such as paramagnetism. And they can transfer over to a ferromagnetic state. A very clear limitation in the current research, however, is the fact that really no one has studied the idea of trying to get a diamagnet into a ferromagnetic state. So that's something that we'd really like to study here. And we think that might be possible to do so. We have a lot of past research, our group, a lot of past research on a material known as iron disulfide or fool's gold, also known as pyrite. And this takes on the pyrite crystal structure shown here. In pyrite, iron takes on a 2+ oxidation state, which has an electronic configuration, which is a fully filled T2G band with an empty EG band. This leads to semiconducting diamagnetic properties. Now, if we look one atom over in the periodic table to cobalt, we see that cobalt can form a material known as cobalt disulfide, and it takes on the same pyrite structure as we'd expect for iron disulfide. And it also takes on 2+ oxidation state. However, because of the addition of an extra electron here, cobalt disulfide actually has a fully filled T2G band with a partially filled EG band, causing it to become a ferromagnetic metal. Now, something really interesting is occurring here. And basically, if we look at the global phase diagram of the transition metal sulfides here, we can see that iron disulfide is sitting in very close proximity to ferromagnetic cobalt disulfide. So in fact, if we begin doping iron disulfide with small amounts of cobalt with as little as 1% cobalt addition, we're able to achieve a ferromagnetic state. This leads to a very fundamental question. Is it possible to actually achieve this transition electrostatically via the induction of electrons on the surface? Because iron disulfide is sitting very close to ferromagnetic instability, we might be able to do that purely electrostatically. So to test this hypothesis, this is the experimental setup that we have. Basically, we have a metallized cylinder that acts as our gate electrode, and it also acts as a holder for our ionic liquid. Then we submerge a semiconducting iron disulfide single crystal in there, and we apply a gate voltage to it, allowing us to induce charge carriers in the sample and get this EDL to form on the surface. So now let's look at some of the experimental results of this study, namely the surface conduction. So if we measure the sheet resistance of our iron disulfide sample as a function of temperature of the system at 0 applied gate voltage, we get a graph that looks like this. There's a little wrinkle here. I won't explain the technicalities of that. The main idea here is that as we get to colder and colder temperatures, this behaves as a semiconductor should. It's increasing, its resistance is increasing exponentially. And as we heat the sample, its resistance is decreasing exponentially, as we expect for semiconducting properties. So if we start applying gate voltages to the sample and get electrostatic charge accumulation, we can see that eventually at low temperatures, these high resistances decrease orders of magnitude to a finite resistance, which is very indicative of achieving an insulator to metal transition in our sample. And also additional studies, additional R versus T studies have found that this is a very reversible and likely a purely electrostatic mechanism that's occurring. I can discuss that later if someone has a question, but we're taken for granted right now. So now another question we might want to pose is that we see this nice transition here, but is there any sort of magnetic states that are accompanying this sort of semiconductor to metal transition? So to actually probe that question, we use the Hall effect as our main probe here. So what we're going to do here is measure the Hall conductance of our sample as a function of applied field. We're doing this at a temperature of 30 Kelvin over a range of applied gate voltages. I want to focus our attention to this figure on the right here. This is basically we're applying low gate voltages to our sample. And we can see that we're getting a negative Hall coefficient to appear. And it's also somewhat of a nonlinear behavior that's appearing here. And we simply attributed that to the fact that maybe some slight magnetization is occurring. But overall, this is likely a generally ordinary Hall effect signal. And it's negative because of the fact that upon application of voltage, we're causing the surface state to become N-type. So we're seeing negative carriers. And then we see Vg equals 0 here. That's giving us an approximately 0 Hall conductance because of the fact that the surface state has very low mobility at that applied voltage. So now let's look at this graph on the left. If we get to higher applied gate voltages, upwards to 3 volts here, we see that some very large sigmoidal shapes with finite saturation and positive Hall coefficients appear. Now, this is very indicative of the fact that an anomalous Hall signal is being the dominant signal here because of how much greater it is than the signals that we're seeing at low voltages. Like I said, we attributed this to the ordinary Hall effect, but the anomalous Hall effect is so much larger and sensitive to the magnetization that when the material becomes more and more magnetized, the signal that we see actually becomes larger. And we see that's happening here with larger and larger applied gate voltages. And this is telling us that we're seeing some sort of magnetization, but we don't necessarily know if it's ferromagnetism. It might be paramagnetism because of the fact that we don't see any open hysteresis loop. Note, we are currently at 30 Kelvin. So to test to see if we can get below the Curie temperature of our sample, we cool the sample down to about 1.8 Kelvin. We perform the same Hall conductance versus field measurements. And here we see then open hysteresis loop with finite coercivity, remnant magnetization, and the saturation is actually seen if we zoom into very low applied fields. So that's a very good sign that we're actually achieving a ferromagnetic state. And this is due to an anomalous Hall signal that's sensitive to the magnetization of our sample. And one thing I want to note is that we're also seeing a positive Hall coefficient here in these high voltage applications. That's very good signs because of the fact that the bulk Hall coefficient in cobalt doped iron disulfide samples, magnetized samples, is actually positive. So it's exactly what we'd expect if we're actually causing this to turn into a ferromagnetic state that's like just adding cobalt atoms to our iron disulfide sample. So we could do some additional characterization here. And we do this by measuring the coercivity of our sample as a function of applied temperature. And what we see here is we have one sample at a gate voltage of 3 volts. And what we're seeing, the main result here is that upon heating our sample, we can see that the coercivity begins to decrease, as we'd expect for a ferromagnet. Basically, we're inducing enough thermal energy into the system to disrupt the exchange energy of the spins that are aligned. So that's what we'd expect for ferromagnetism. So now what we're doing here is we're introducing a different iron disulfide sample, just basically a different grown crystal, and applying a voltage to it. And we see here the main result is that upon greater voltage application, the Curie temperature of the sample actually increases, which is expected in the sample because of the fact that upon greater voltage applications, we're getting higher charge densities in our sample. And that's logistically just like adding more electrons to our iron disulfide. It's like doping it with more cobalt. And then if we throw in another sample, this is just something I like to throw in because of the fact that it shows that the types of iron disulfide samples that we grow are somewhat random in the fact, but we see here that we are able to achieve a 25 Kelvin max Curie temperature with ranges between 10 and 25 Kelvin. So that's what we got there. So with that, that's basically everything that I'd like to talk about. But I'd also like to end on the note that, in summary, our group was very successful in establishing that semiconducting diamagnetic iron disulfide single crystals with a zero spin electronic configuration is very capable of being electrolyte gated into a ferromagnetic metallic state using only voltage. This result is something that no other research group to date has been able to do, or at least publish. And because of that, we were able to publish our results in a very high output journal, Science Advances. And because of this novel discovery that we made here, we were actually able to get a lot of really unique national attention on this research, such as being featured in Popular Mechanics and Fox News articles, as well as a few national sources. So with that, I'd like to thank you all for coming to my talk today. And if you have any questions, I'd be happy to answer them at this point.
Okay, thank you so much. Timing was great. I have a question. I think I might lead with this question for every speaker. So guess what? You get it first. Why would NASA be interested either in the results or in somebody being able to do this kind of experimentation?
Well, NASA, as I understand, is very interested in fundamental science that leads to possibilities of new, really exciting research applications. I think NASA would be interested in this because of the fact that this is an incredibly novel result that no one has seen yet. The idea that you can take something that has no net spin and use only electrostatic methods, very low energy, I might add, because of the fact that we're using voltage, and turn that into a ferromagnetic state. This has very unique tangible applications to the next generation electronics development in the terms of creating non-volatile, high efficiency transistors, sort of in a sense of functionalizing modern transistors to circumvent the problem of Moore's law that we're currently encountering. So novel solutions.
Okay, thank you. I don't see any questions in the chat yet, so I'm just going to try one more right now. I'm a low temperature physicist myself by training. Where did you do this? Does Augsburg have the ability to get you down to 1.8 K?
Oh, that was my question.
Yeah, no, that's a great question, because we currently do not have that capability. As I noted at the beginning of my talk, I did this in the summer of 2019. So I actually performed this research with my advisor, Dr. Jeff Walter, and his old PhD advisor, Dr. Chris Layton's lab at the U of M. So we did it in a cryostat. And that's one of the main reasons why we utilize the Hall effect to measure the magnetization, because it's sensitive to it. We weren't in an actual magnetometer, so we had to use something else to do that.
Did you use that PPMS?
I'm sorry?
The instrument you used was the PPMS for quantum design?
I'm not too sure. I'm
Okay.
sorry to not be able to give you a finite
That's
answer.
fine.
But actually, maybe the two of you could follow up if you're interested, because Thelma is into magnetism and magnetism experiments. But we better go on. Thank you so much. Why don't you stop sharing your screen?
Yep, thank you.
Okay, so I'm going to stop this recording and restart it for the next speaker.